Today we present a pyramid transformer for traffic sign detection. Automatic detection and classification of traffic signs have become an essential asset in the visual system of autonomous vehicles and self-driving cars. Recently, vision transformers have achieved remarkable response on various benchmarks of visual tasks. We observed that prior which could not provide satisfactory gain in traffic sign detection because the dataset size of this task is very small and the class distribution of traffic signs is highly unbalanced. To solve the problem, we propose a novel pyramid transformer with a hybrid architecture in this paper. Specifically, pyramid transformer follows a hierarchical architecture to build a feature pyramid with local and global information by using atrus convolution. Furthermore, it inherits an intrinsic inductive bias and aims to learn multi-scale feature representation for objects of varying size, thereby enhancing the network robustness against the size discrepancy of traffic signs. We conduct experiments on the German traffic sign detection benchmark GTSDB, which result demonstrated the superiority of the proposed model in the traffic sign detection tasks. Traffic sign recognition and detection (TSRD) are crucial to driver assistance systems and self-driving cars. One of the main prerequisites for the widespread implementation of TSRD is an algorithm that is robust, reliable, and high accuracy in various real-world scenarios. Besides the large variation in traffic signs to detect the traffic image taken on the road are not idle. They are often distorted by the camera motion, challenging weather conditions, and poor lighting conditions that significantly make it difficult to deploy in real scenarios. TSRD is still a challenging study and several work have been conducted on it. TSRD consists of two independent branches, traffic sign recognition (TSR) and traffic sign detection (TSD). Traditionally, the methods of TSD usually depend on manual feature extraction. Features are extracted manually from different attributes, including edge detection, color information, and geometric shapes. Occur because of the camera movements during live video streams. Disorientation, scale variation, and occlusion of traffic sign region hinder the practical application of this approach. In contrast, TSR methodologies use convolutional neural networks (CNN) to extract deep features. Unfortunately, until today, there is no comprehensive model to describe the best classifier and the perfect feature extraction backbone for TSR. In this study, we particularly focus on designing a new backbone for traffic sign detection. As far as we know, no previous studies have applied a vision transformer to this specific task. The transformer was first introduced in the field of natural language processing, which is a deep neural network based on a self-attention mechanism. In contrast to the traditional recurrent neural networks and convolutional neural networks, transformer is an attention-only structure without recursion or convolutional operation, which improve a parallel efficiency without sacrificing the performance. Vision transformers are established as a novel backbone for vision-related issues. Transformers have emerged with encouraging performance in computer vision tasks, and their structures are under development. Therefore, we introduce a novel pyramid transformer enhanced by locality inductive bias and pyramid module, which combine two kinds of basic block: pyramid block and normal block. Pyramid blocks help to downsample and embed the input image into the patch with strong multi-frequency features, while the normal blocks attempt to jointly capture local and hierarchical global attributes in the patch sequence. Furthermore, each block consists of two parallel branches, including a parallel local self-attention and convolution layer combined by a feed-forward network. Significantly, pyramid block has an additional pyramid module which compresses address convolution with different dilation rates to capture a local and global feature into the token. This section provides an overview of our model and then describes the proposed pyramid transformer architecture in details. As overview of our architecture, pyramid transformer aim to introduce the pyramid structure into the vision transformer, so that it can generate multi-scale feature maps for dense prediction tasks. As shown in figure, the proposed architecture is composed of two types of blocks: pyramid blocks and normal blocks. The function of pyramid blocks is to embed multi-scale context into tokens, and normal blocks are used further to inject a convolutional bias into the transformers. Figure shows that pyramid transformer offers 4 stages to downsample an input image, where 4 pyramid blocks are used to reduce the feature gradually by 4 times and 2 times into the end, respectively. At each stage, several normal blocks are sequentially grouped following the pyramid block. Note that all of the normal blocks in each group have the same isotropic design. The number of normal cells determines model parameters and size. Using this method, pyramid architecture can extract a feature pyramid from different stages F1, F2, F3, and F4, which is used by the decoder head designer for detection tasks. Pyramid block. In each stage, pyramid blocks are employed to embed local information and multi-scale feature into the token rather than immediately splitting and flattening images. It uses a linear patch embedding layer, which introduces intrinsic inductive bias scale invariance from convolution. In figure, the PB is divided into the 2 parallel branches, which together model long-range and local dependency, attended by a feed-forward network that transforms the feature. The input image is the input for the first pyramid block. As shown in the figure, in the branch of global dependency, firstly, image enter a pyramid reduction module PRM for multi-scale context extraction. After pyramid module, MHSA module process the feature map to model long-range dependencies, and moreover, we embed a local context through a parallel convolutional module, PCM. PCM consists of a sequentially stacked convolution layers, batch normalization, and an image to sequential operation. Furthermore, parallel convolutions use straight convolutions to match the PRM's spatial downsampling ratio. As a result, the token features learn both low-level and multi-scale information, implying that a pyramid block occurs a local and intrinsic inductive bias by design. Feed-forward network process the fused token, and after the resulting sequence is converted to the feature maps. This feature feed into the following pyramid block or normal block by design. Normal block. As shown in the picture, normal blocks have a similar structure to pyramid blocks, except that there is no PRM in normal blocks. As I told on the past section, because feature maps after pyramid blocks have relatively small spatial dimensions, PRM is not indexed in normal blocks. The class token from the third pyramid block is concatenated with feature map from the third pyramid block, and then combined with positional embedding to resolve the input paths for the next normal blocks. Class tokens are randomly generated at the beginning of the training phase and stay the same during the procedure. The tokens are pushed into the MSA module in the same way as the pyramid block. The resulting sequence is transformed into the feature maps during this process and then fed into the PCM. Notably, the class token is discarded because PCM has no spatial connection to other visual tokens. And also stack convolution are used in PCM to further reduce the parameter in normal block. And also an element-wise sum is then applied to the features from MSA and PCM. And finally, the feed-forward network process the result tokens to obtain the output features of normal block. We aim to evaluate our pyramid transformer by utilizing two representative meta-architectures, faster RCNN and cascade RCNN. Particularly, our transformer architectures is used to generate the backbones of these frameworks. As a fair comparison, we similarly train all the models under the same scheme. Also, we train to make a competitive setting for following works. Further, we show a detection result on GTSTB dataset in table 1 with a standard schedule 36 epochs. All hyperparameters follow a default setting used by Swin. We commonly follow the multi-train scheme to randomly resize the input image so that its longer dimension is less than 1333, while the shorter dimension is between 800 and 480. Table 1 summarizes the result showing that pyramid transformer achieved the best performance while requiring the least number of parameters. Thanks to the introduced pyramid module and locality inductive bias with faster RCNN as decoder for 36 epoch settings, the proposed model achieved 8.1% average precision for 50 IOU and 7.3% average precision for 75 IOU and 6.8% average precision performance gain over swing. It also considerably outperforms other backbones like ResNet and PVT, owing to our model's efficient structure design. From Table 1, our method has the highest MAP when using Cascade RCNN as the decoder, obtaining a 77.8% average precision, 81.8% average precision for 75 IOU and 96.5% average precision for 50 IOU when training only 36 epochs, which our method improved 2.1 mean average precision on faster RCNN and 2.4% mean average precision on Cascade RCNN. The superiority of the pyramid transformer is due to the fact that introducing inductive bias into the pyramid feature module helps our model better utilize the data to further improve performance for object detection. In this paper, we introduced a novel vision transformer based on two-stage frameworks for traffic sign detection, which integrates spatial structure and local information into the vision transformers using two basic blocks that include pyramid blocks and normal blocks. Meanwhile, the multi-scale pyramid features from our model can be applied to various lens prediction visual tasks. Experimental evaluation on the GTSTB dataset proved that our pyramid transformer attains a better performance compared to the state-of-the-art studies. Our next steps will be to investigate more traffic signs from classes that are seldom seen in this benchmark. We also plan to enhance the speed of the process in order to run it on embedded device in real time. I sincerely appreciate your attention today. Thank you.